Chemical properties. Chemical properties. Halogens chemically very reactive. Reactivity decreases with rise in atomic number. Okay. Halogens are chemically very reactive. Halogens are chemically very reactive. Okay. Reactive. Reactivity decreases. Reactivity decreases. Reactivity decreases with rise in atomic number. Rise in atomic number. Atomic number. With rise in atomic number. Okay. Reactivity decreases with atomic number rise. Okay. With rise atomic number. Okay. The reactivity has the order. Reactivity has the order fluorine is the greater than chlorine is the greater than bromine is the greater than iodine. Okay. Chemical reactivity. Chemical reactivity. Chemical reactivity. Halogens are chemically high reactive. Halogens are chemically high reactive. Okay. Halogens are chemically high reactive. Like alkali metals, fluorine is the most reactive element and reactivity decreases. Fluorine is the most reactive element and reactivity decreases with increase in atomic number. Hence, iodine is least reactive. Fluorine is most reactive. Fluorine is most reactive. Fluorine is most reactive and iodine is least reactive. Iodine is least reactive. Iodine is least reactive. Okay. The chemical reactivity of halogen may be explained as following examples. Okay. First one, displacement. When a lower atomic number halogen is passed into halide solution or a higher atomic number, halogens of the higher atomic number is displaced. Okay. When lower atomic number is halogen, halogen is passed into halide solution of higher atomic number, halogens of higher atomic number is displaced. Okay. When lower atomic number halogen is passed lower atomic number halogen is passed. When lower atomic number halogen is passed into halide solution of a higher atomic number halogens of higher atomic number is displaced. Halogens of higher atomic number is displaced. Okay. Fluorine displaces all other halogens from their salts. Chlorine displaces bromine, iodine, while bromine can only replace iodine. As example, fluorine fluorine displaced, fluorine displaced all halogens 2kx plus fluorine, that is 2kf, and displaced halogens. Okay, x equal to chlorine, bromine, iodine, chlorine, bromine, iodine, chlorine, bromine, iodine. Okay. Chlorine 2kx plus fluorine, okay, potassium halide, okay, plus fluorine reactive, then we receive potassium fluoride, and fluorine is removed through halogens x2. Halogens x2 means chlorine, bromine, and iodine, chlorine, bromine, and iodine. Okay, and as example 2kCl plus fluorine, 2kF plus chlorine. Okay, and bromine, 2kCl plus F2, 2kCl plus F2, 2kF plus Cl2 chlorine, and 2kBr plus fluorine, that 2kF plus Br2 removed. Okay, and 2ki plus fluorine, that make 2ki plus I2. So 2kF plus I2. Okay, I2. Okay, iodine is replaced. Okay, iodine is replaced by fluorine. Okay, then all of halogens is replaced by fluorine, because fluorine is most reactive as compared to another halogens. Okay, then this is chlorine, and after fluorine, next element of halogens is chlorine. Okay, chlorine. Okay, chlorine is removed to fluorine, bromine, iodine. Okay, bromine and iodine. Okay, that 2kBr. Okay, potassium bromide plus Cl2 chlorine, and that make 2kCl plus Br2. Okay, bromine is replaced by chlorine. Okay, and 2Ki potassium iodide plus Cl2 chlorine, and that make 2kCl plus I2. Okay, and next element bromine. Okay, bromine. Then bromine 2Ki potassium iodide plus bromine, that make 2kBr potassium bromide plus iodine. Okay, iodine cannot replace any halogens from their salts. So we discussed about this theme. Then we achieve iodine. Iodine cannot replace any halogens from their salts, from their salts. Okay, from their salts. Okay, second point, reaction with water. Second point, reaction with water. Okay, reaction with water. Halogens decompose water, giving oxygen. Fluorine is a strong oxidizing agent, and it oxidizes H2O plus O2. Okay, as example, F2 plus H2O, that makes 2 hydrogen fluoride 2HF plus half O2 plus half O2, 2HF plus half O2, okay? And chlorine and bromine disproportionate water. Chlorine and bromine disproportionate proportionate water, okay? Chlorine plus H2O that make HCl, hydrogen chloride plus HOCl, hydrogen hypochloride, HOCl, and H2O plus Br2 that make HBr plus HOBr, okay? Iodine does not react with water due to its weakest oxidizing property, okay? Iodine does not react with water. Iodine does not react with water. Iodine does not react with water due to its weakest oxidizing property. Due to its weakest oxidizing property. Oxidizing property, okay? Next point, reaction with alkalis, okay? Next point, reaction with alkalis. 1 minute. Reaction with alkalis. Reaction with alkalis. Reaction with alkalis, okay? Reaction with alkalis. Fluorine reacts with alkalis violently, giving fluoride and oxygen, okay? Fluorine reacts with alkalis violently, giving fluorides and oxygen, okay? 2NaOH plus fluorine. Fluorine reacts with alkalis violently, giving fluoride and oxygen. 2NaF plus H2O plus half O2. Okay? Chlorine, bromine, iodine from NaX and NaOX with cold water dilute alkalis. Chlorine, bromine and iodine from NaX, sodium halide, and NaOX, okay, with cold and dilute alkalis okay, cold and dilute okay, cold and dilute 2NaOH plus Cl2 that make NaCl plus NaOCl plus H2O, okay, 2NaOH plus Br2 that make NaBr plus NaOBr plus H2O. 2NaOH plus iodine that make NaI, sodium iodide plus NaOI plus thus the general reaction is 2NaOH plus X2 that make NaX plus NaOX plus H2O where X equal to chlorine, bromine and iodine. Okay, and chlorine, bromine and iodine form NaX and NaXO3 with hot and concentrated alkali. With hot and concentrated alkalis. Okay, hot concentrated hot concentrated 6NaOH plus 3Cl2 that 5NaCl plus NaClO3 plus 3H2O. Okay, 6NaOH plus 3Br2 that make 5NaBr plus NaBrO3 plus 3H2, 6NaOH plus 3I2, 5NaI plus NaIO3 plus 3H2O. Thus the general reaction is as given below. Thus the general reaction is as given below. 6NaOH plus 3H2 that make 5NaX plus NaXO3 plus 3H2O where X equal to chlorine, bromine and iodine. Okay, chlorine, bromine and iodine. Okay, next studying reaction with halogen. Okay, reaction with halogen. 1 minute. Reaction with halogen. Reaction with hydrogen. Okay, reaction with hydrogen. All halogens combine with hydrogen to form halogen acids or gaseous hydrides. Okay, all halogens combine with hydrogen to form halogen acids are gaseous hydrides. Okay, H2 plus H2 that make 2HX where X equal to chlorine, bromine and iodine. Okay, all these hydrides, hydrogen chloride, hydrogen bromide, hydrogen iodide, are highly soluble in water and give strongly acidic solution. Chlorine reacts most vigorously with hydrogen while iodine reacts least vigorously slowly. Okay, combination with metals. 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 Okay. Most of the metals form halides with halogen. Most of the metals sodium, potassium, magnesium, zinc, ferrous, etc. form halides with halogens. Okay. 2 sodium plus chlorine that make 2 NaCl. Zn plus Cl2 that make ZnCl2, and 2Fe plus 2I2 that make 2FeI2, and 2K plus I2 that makes 2Ki. Okay. Combination with non-metals. Combination with non-metals. Okay. Some of the non-metals, sulfur, fluorine, arsenic, etc. also combine with halogen forming halides. They have a little affinity for O2 oxygen and form a few oxides which are extremely unstable. For example, sulfur form a fluoride with fluorine like SF6, SCl4 with chlorine, and SbR2 with bromine, and does not react with iodine. Okay, sulfur hexafluoride is a extremely stable halide of sulfur. Phosphorus form of PCl5, PCl3, PbR3. Okay, and generally the halides formed by combination of non-metals are covalent in nature. Next, 7 point, reaction with hydrocarbons. Reaction with hydrocarbons. Okay. All halogens react with hydrocarbon reactally decreases from fluorine to iodine. Fluorine dissociates the hydrocarbon as fluorine dissociates the hydrocarbons as methane CH4 plus 2F2, that is 4HF plus carbon. Chlorine and bromine displaces hydrogen, but iodine does not react with hydrocarbons. Okay. Chlorine and bromine displaces hydrogen. But iodine does not react with hydrocarbons. hydrocarbons. Hydrocarbons, okay? Methane CH4 plus 4Cl2. That makes CCl4 plus 4HCl. 4HCl, okay? And methane CH4 plus 4Br2. That makes CBr4 plus 4HBr, okay? And methane plus 4I2. No reaction. No reaction. Okay? The above discussion clearly indicates that fluorine is most reactive of the halogens. It reacts with all other elements except helium, neon and argon. The high reactivity of fluorine is due to low energy of fluorine-fluorine bond oxidizing power. Small size and high electronegativity. The small size of the ions leads to a high coordination number and thus have a high lattice energy of the crystal. In addition to this, the high electronegativity values results in very strong bond with other elements. Okay, fluorine has the distinction property of bringing out the highest valence state of an element, PF6, SF6, OSF8 and IF7. Okay. Next is hydrogen halides. Hydrogen halides are hydra acids. Hydra acids. Okay. Halogen halides. That means hydra acids. All the halogens react with hydrogen and form HX. All the halogens react with hydrogen. All the halogens react with hydrogen and form hydrogen halide or hydra acids, which are called hydra acids, which are called hydra acids. Okay. Then H2 plus H2, that is 2HX. Okay, hydra acids. Okay. Fluorine react with hydrogen, which explosion even in dark at very low temperature. Okay. Fluorine reacts with hydrogen, with explosion even in dark at very low temperature, approx minus 210 degrees Celsius. Okay. Then hydrogen plus fluorine, hydrogen fluoride plus 128 kilocalories energy. Okay. Other halogens react with hydrogen on heating and in the presence of a suitable catalyst. Chlorine react with hydrogen in the exposure of sunlight, while bromine reacts with hydrogen upon heating. Iodine reacts with hydrogen to a certain extent only when heated in the presence of PT as catalyst. This shows that reactivity decreases with increase in atomic number. Okay. Properties of hydra acids. Properties of hydra acids. Property of hydra acids. Okay. First point. physical state. Physical state. First point, physical state. Property of hydra acids. First, physical state. Physical state. Okay. First physical state. Okay. First physical state. Okay. Hydrogen chloride, hydrogen bromide, and hydrogen iodide are gases in normal. Hydrogen chloride, hydrogen bromide, hydrogen iodide are gases in normal conditions. Gases in normal condition. Gases in normal condition. Okay. Gases in normal condition. Okay. And while hydrogen fluoride is a liquid, and while hydrogen fluoride is a liquid. Okay. Due to presence of strong hydrogen bonding. Due to hydrogen bonding, boiling point of hydrogen fluoride is also high. Due to strong hydrogen bonding. Due to strong hydrogen bonding. Due to strong hydrogen bonding, boiling point of hydrogen fluoride is also high, approx 19.9 degrees Celsius. Second point, stability. Second point, stability. Okay. Stability. On moving down the group, the hydrogen halide bond strength decreases from hydrogen fluoride to hydrogen iodine. Okay. Hydrogen iodide. Okay. On moving down the group, the HX bond strength, the HX bond strength decreases from hydrogen fluoride to hydrogen iodide. Okay. Hydrogen fluoride is the most stable, while hydrogen iodide is the least stable hydrogen halides. Okay. This is explained on the basis of dissociation temperature. Hydrogen fluoride and hydrogen chloride are not dissociated even at 1200 degrees Celsius, while HBr is dissociated 1% and hydrogen iodide is dissociated 20% at 400 degrees Celsius. Okay. Next point, reducing property. Reducing property. Okay. As radius size increases, the stability of hydrogen halide bond decreases and reducing property increases in same order. Thus, the reducing property of hydra acids of halogens increases in the order of given below. Hydrogen fluoride is less than hydrogen chloride, is less than hydrogen bromide, is less than hydrogen iodide. Okay. Hydrogen iodide. This is the reducing property of hydra acids of halogens increases in order of given. Okay. Second, so hydrogen fluoride is not reducing agent. So hydrogen fluoride is not reducing agent. Hydrogen fluoride is not reducing agent, while Hydrogen chloride is a mild reducing agent. Mild reducing agent. Mild reducing agent, and hydrogen bromide HBr is stronger reducing agent, while hydrogen iodide is strongest reducing agents, strong reducing agents. Okay. Reducing agents of hydrides of halogens. Okay. Of hydrides of halogen. Okay. Next one, nature of hydrogen halide bond. Okay. Nature of hydrogen halide bond. Okay. Next, nature of hydrogen halide bond. Okay. Nature of hydrogen halide bond. Nature of hydrogen halide bond. Okay. Nature of hydrogen halide bond. Okay. Nature of hydrogen halide bond. All the halides are covalent compounds. Having some ionic character. The extent of ionic character depends upon the electronegativity value of halogen. More will be the value of electronegativity, higher will be the ionic character. Their ionic character as the order as given. Ionic character order. Ionic character order. Hydrogen chloride is greater than hydrogen chloride, is greater than hydrogen bromide, is greater than hydrogen iodide. Okay. These halides possesses low melting and boiling points, which indicates their covalent character. These halides possesses low melting and boiling points, which indicate their covalent character. Which indicate their covalent character. Okay. Next heading, relative acidic strength. Relative acidic strength. Relative acidic strength. Okay. Relative acidic strength. Okay. Acidic strength of hydric acid is given below. HF is less than HCl, is less than HBr, is less than HI. Okay. Acidic strength of hydric acids. Okay. As radius of X negative increases. Okay. Radius of X negative increases. Attraction of X negative with hydrogen plus decreases. Then attraction of halogen negative with hydrogen positive decreases. Okay. Dissociation of hydrogen halide HX to H plus X negative increases, and acidic strength increases, and acidic strength increases. Hence, hydrogen iodide is the strongest acid among the hydrogen halogen. Okay. Okay, hence, 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 hydrogen iodide is the strongest acid. Is the strongest strongest acid strongest acid among hydrogen halogen. Okay, hydrogen halogen bond. Okay, it may noted that hydrogen iodide is the strongest reducing agent also among HX. Okay, it may be noted that it may be noted that it may be noted that hydrogen iodide is the strongest reducing agent strongest reducing agent also among HX, also among HX. Okay, all hydrides of hydrogen ionize in water and behave as acids. Hydrogen chloride is the weakest, while hydrogen iodide is the strongest acid among the hydra acids. The relative acidic strength can be explained on the basis of the relative hydrogen bond strength. The hydrogen bond strength has the order hydrogen iodide is less than hydrogen bromide, is less than hydrogen chloride, is less than hydrogen fluoride. This is the relative acidic strength can be explained on the basis of the relative halogen bond strength. Okay, this is the halogen bond strength has the order of hydrogen halogen bond. Okay, HX bond. Okay, hence hydrogen iodide easily dissociates, due to which it behaves as the strongest acid, while hydrogen fluoride does not dissociate easily, therefore it behaves as the weakest acid. Okay, hydrogen iodide and hydrogen fluoride easily dissociated. Hydrogen iodide easily dissociates, easily dissociates due to which behaves as strongest acid, acid, while hydrogen fluoride HF does not dissociate easily, does not dissociates easily, therefore its behave as a weakest acid. Okay, next is hydrogen bonding. 6 point hydrogen bonding. Okay, hydrogen bonding. Okay, hydrogen bonding. Hydrogen fluoride shows strong hydrogen bonding, while other hydra acids of hydrogen do not show hydrogen bonding. Okay, hydrogen fluoride shows strong hydrogen bonding. Hydrogen fluoride shows strong hydrogen bonding. Strong hydrogen bonding. Okay, hydrogen fluoride shows strong hydrogen bonding, while other hydra acids, while other hydra acids, while other hydra acids of halogen do not show. Of halogen do not show, do not show, do not show hydrogen bonding. Hydrogen bonding, okay? Hydrogen bonding. Hydrogen fluoride show strong hydrogen bonding, while other hydra acids of halogens do not show hydrogen bonding, okay? Hydrogen bonding in HF, hydrogen bonding in HF, okay? 1 minute. Hydrogen bonding in HF. Hydrogen bonding, hydrogen bonding in HF. Hydrogen bonding in HF, okay? Hydrogen bonding in HF. Hydrogen bonding in HF, okay? Hydrogen fluoride is a polar molecule. Hydrogen fluoride is a polar molecule. HF is a polar molecule. HF is a polar molecule, okay? Okay. H positive, fluorine, delta negative, okay? HF is a polar molecule. Due to high electronegativity, due to high electronegativity, difference between fluorine and hydrogen, difference between fluorine and hydrogen and a small size of fluorine of positive end of one molecule is attracted by the negative end of the other molecules, okay? Hydrogen fluoride, HF plus delta minus delta, okay? Dot hydrogen plus delta, fluorine minus delta, that is HFX, okay? And hydrogen bonded chain in solid HF is, you can show 1 minute. Fluorine, hydrogen, fluorine, hydrogen, fluorine, hydrogen, hydrogen, fluorine, hydrogen, fluorine, hydrogen, fluorine, hydrogen, okay? This is the hydrogen bonded chain in solid HF. This is the hydrogen bonded chain in solid HF, okay? Solid HF. The bond energy of hydrogen bond in hydrogen fluoride is 29 kilojoule per mole. Bond energy of hydrogen fluorine, hydrogen is 29 kilojoule per mole, okay? Due to hydrogen bonding, hydrogen fluoride behaves as HFS. Its molecular weight is high and so its boiling point is high. The strength of hydrogen bond in hydrogen fluoride is strongest relative to that in water, ammonia. Due to large size of chlorine, there is no hydrogen bonding in hydrogen chloride, okay? Due to hydrogen bonding, due to hydrogen bonding, due to hydrogen bonding, due to hydrogen bonding, HF2 negative, HF plus fluorine negative, triple bond fluorine, hydrogen, fluorine negative, minus delta plus delta, exist and due to lack of hydrogen bonding exists and due to lack of hydrogen bonding HCl negative 2 does not exist. Okay, the important property of hydra acid are summarized. Then state property hydrogen chloride property hydrogen fluoride, hydrogen bromide, hydrogen iodide. Okay, state. This is liquid, hydrogen chloride gas, hydrogen bromide gas, hydrogen iodide gas. Okay, and molar weight is 19.008, 36.467, 80.928, 127.5. Melting point degree Celsius minus 83.1, minus 114.22, and minus 86.9, minus 50.8. And boiling point 19.9, minus 85.0, minus 66.7, minus 35.4. Density reducing agent stability most stable, high stable, least stable. Okay, reducing agent. Okay, not reducing agent, weak reducing agent, strong reducing agent, strongest reducing agent. Okay, acidic strength, weakest, stronger, strongest. Okay, hydrogen bond, maximum hydrogen bond, very less, least hydrogen bond, okay. Next heading oxides. Okay, oxides. Okay, as electronegativity of oxygen is 3.5 while that of fluorine is 4. Okay, arsenic electronegativity of oxygen as electronegativity of oxygen is 3.5 while that fluorine is 4. Hence the binary compounds found by the combination of halogen with oxygen are called oxide except fluorine. These binary compounds of oxygen with fluorine are called fluoride. Okay. As electronegativity of oxygen as electronegativity of oxygen is 3.5 while that of fluorine is 4.0, hence binary compounds formed by the combination of halogen, hence binary compounds formed by the combination formed by the combination of halogens with oxygens are called oxides except fluorine. The binary compounds of oxygen with fluorine are called fluoride. Example F2O, oxygen difluoride, oxygen difluoride, oxygen difluoride, F2O2 dioxygen difluoride, okay. Halogens do not react directly with oxygen. Halogens do not react directly. Halogens do not react directly with oxygen, due to which their oxides are prepared by indirect methods. Okay. First point, oxides of fluorine. Oxides of fluorine. Okay. Two oxides of fluorine will known as, for example, first oxygen difluoride, oxygen difluoride, okay. OF2, oxygen difluoride is prepared by passing a fine stream of fluorine through solution. 2NaOH plus F2, that make 2NaF plus H2 plus OF2 gas, okay. Oxygen difluoride. It is also prepared by dissolving fluorine nitrate in 2% of sodium hydroxide solution. It is also prepared by dissolving fluorine nitrate in 2% sodium hydroxide solution. Okay. 2 sodium hydroxide NaOH plus 2 FNO3, that make 2 NaNO3 plus H2O plus OF2. Okay. OF2 is a fairly stable colorless gas. OF2 is a fairly fairly stable, colorless gas having a strong smell melting point, having a small having having a strong smell, having a strong smell, having a strong smell, melting point minus 224 degrees Celsius and a boiling point 145 degrees Celsius. It is slightly soluble in water. It is slightly soluble. It is slightly soluble in water. It is slightly soluble in water. It is a powerful oxidizing agent. It is a powerful. It is powerful oxidizing agent. Powerful oxidizing agent and liberates iodine and liberates iodine from a solution of potassium iodide. Okay, then OF2 oxygen difluoride plus 4Ki potassium iodide plus water that make 2KF potassium fluoride plus 2KOH potassium hydroxide plus 2I2. Next, dioxygen difluoride. Difluoride. 1 minute. Dioxygen difluoride. Dioxygen difluoride. O2F2. It is prepared by the action of electric discharge in a mixture of fluorine and oxygen at low pressure 10 to 20 mm. Okay, then F2 plus O2, that is O2F2 minus 180 degrees Celsius. It is prepared by the action of electric discharge. Electric discharge in a mixture of fluorine and oxygen at low pressure 10 to 20 mm pressure. 10 to 20 mm pressure. Okay, it is very unstable. Very unstable. It decomposes into fluorine and oxygen event. It decomposes into fluorine and oxygen even at minus 100 degrees Celsius. Okay, fluorine also form other oxides. Fluorine also form other oxides like FO, F2O3 and F3O4 etc., which are unstable. Okay, next point, do oxides of chlorine. Okay, following oxides of chlorine are well known: Cl2O, chlorine monoxide, chlorine monoxides, and ClO2, chlorine dioxide, chlorine dioxide, chlorine oxide Cl2O6, chlorine hexoxide, chlorine hexoxide, and Cl2O7, chlorine heptoxide, chlorine heptoxide, chlorine heptoxide. First point, chlorine monoxide, chlorine monoxide, chlorine monoxide, Cl2O. When freshly prepared HGO is treated with a chlorine gas, Cl2O is obtained. 2HGO plus 2Cl2 that make HGO into HgCl2 plus Cl2O. Cl2O. It is brown yellow gas. It is brown yellow gas having boiling point 2 degrees Celsius. It is thermally unstable and explodes on heating. It is thermally unstable. And explodes on heating. Okay. Then 2Cl2O on heating, O2 plus 2Cl2. It dissolve in water. It dissolve in water. It dissolves in water, forming hypochlorous acid. Okay. Acid. It dissolves in water, forming hypochlorous acid. Okay. Then Cl2O plus H2O that make 2HOCl. Okay. And this is a hypochlorous acid. Hypochlorous acid, HOCl, hypochlorous acids. Okay. Chlorine dioxide. Okay. Chlorine dioxide, ClO2, chlorine dioxide. It is prepared by the action of concentrated sulfuric acid on potassium chlorate. Okay. 3KClO3 plus 3H2SO4, that is HClO4 plus 3KHSO4 plus H2O plus 2Cl2O2. Okay. Yes. As there is a chance of explosion in this reaction, ClO2 is prepared by heating KClO3 with oxalic acid. Okay. Then 2KClO3 plus 2H2C2O4 oxalic acid that make K2C2O4 plus 2H2O plus 2CO2 plus 2ClO2. Okay. The best method of preparation is by heating AgClO3 with chlorine gas. 2AgClO3 plus 2Cl2 that make 2AgCl plus 2ClO2 plus O2. It is yellow gas. It is yellow gas. It is yellow gas. Yellow gas. It is yellow gas with a unpleasant smell. With a unpleasant smell and unpleasant unpleasant smell. Okay. It has a commercial importance due to its superior bleaching properties. It has commercial it has commercial importance. It has commercial importance. It has commercial importance due to its superior bleaching properties. Okay. Third point, chlorine oxide. Chlorine oxide chlorine hexoxide. Okay. Chlorine hexoxide, Cl2O6. Chlorine hexoxide. When chlorine dioxide is treated with ozone, and chlorine hexoxide is obtained. Okay. 2Cl2, chlorine dioxide. This is chlorine dioxide plus ozone, that makes Cl2O6 plus half O2. Okay. It is dark red liquid. It is dark red liquid. It is dark red liquid. It is also explosive and it decomposed to CO2 and oxygen. Okay. Cl2O6, 2Cl2 plus O2. Okay. It also dissolve in water. It also dissolve in water. Okay. Cl2O6 plus H2O, that makes HClO3 plus HClO4. Okay. Then a chlorine heptoxide. Fourth point, chlorine heptoxide. Chlorine heptoxide, Cl2O7, chlorine heptoxide. When HClO4 is dehydrated with P2O5 at low temperature, approx minus 10 degrees Celsius, then Cl2O7 is formed. Okay. Then 2HClO4 dehydrated plus P2O5, that makes Cl2O7 chlorine heptoxides plus P2O5 into H2O. Okay. It is a colorless or oily liquid. It is colorless chlorine heptoxide, colorless, highly liquid, colorless, highly liquid. It is a explosive but most stable oxide of chlorine. It is explosive, 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 most stable oxide of chlorine. Most stable oxide of chlorine. Most stable oxide of chlorine. It dissolves in water and form HClO4. It dissolves in water and form HClO4. Okay, Cl2O7 plus H2O. That makes 2HClO4. Next, oxides of bromine. Oxides of bromine. Okay. Next, oxides of bromine. Okay. Oxides of bromine. Okay. Oxides of bromine. Bromine forms three well-known oxides. First, Br2O, bromine monoxide. Bromine monoxide. Bromine monoxide gas and stable below minus 40 degrees Celsius. Second point, BrO2, bromine dioxide. Bromine dioxide. It is yellow solid stable. It is yellow solid stable below minus 40 degrees Celsius. Third point, Br3O8, that makes bromine peroxide. Bromine peroxide, white crystalline solid stable below white crystalline solid stable below minus 80 degrees Celsius. Okay. Oxides of iodine. Fourth point. Oxides of iodine. Iodine also forms three oxides. First, IO2 or I2O4, iodine dioxide. This is the stablest oxide of I2. It is prepared by heating iodic acid at 200 degrees Celsius. Iodic acid 2HiO3 at 200 degrees Celsius, and that make I2O5. Sorry, this is iodine dioxide lemon yellow powder. Iodine dioxide lemon yellow powder. Okay, lemon yellow powder. And the second point, I2O5. Okay, Then that make I2O5 plus H2O. H2O. Okay. This is the established oxide of iodine. Okay, it is prepared by heating. Iodic acid at 200 degree Celsius temperature. It is white stable solid. It is white color, white stable solid. It is white stable solid, and melting point 300 degree Celsius. It has melting point 300 degree Celsius. It decomposes and heating into iodine and oxygen. 2I2O5. After heating, it is decomposed in iodine and oxygen. Okay. Third point. I4O9 iodine oxide. Pale yellow powder. It is pale yellow powder. Okay. Powder. Higher oxides of halogenous are comparatively more stable than lower oxides. Okay. Higher oxides of halogenous are comparatively more stable than lower oxides. Okay. Structure of oxides. Structure of oxides. Okay. Structure of oxides. Hence, structure of F2O, Cl2O and Br2O is tetrahedral, but their shapes are angular. The structures of these monoxides you can show. One S, 2S, 2P. Oxygen atom. Okay. That is lone pairs. sp3 hybridization bond pairs. That is bond pairs. Okay. Then oxygen, fluorine, and this is 103 degrees Celsius, 1.41 angstrom, and oxygen, chlorine, 111 degree and 1.71 angstrom. Bond length 1.7 angstrom and bond angle 111. And oxygen, bromine, and it is less than 111 degree. Okay. Next, studying the structure of I2O5 and Cl2O7 are given. You can show 1 minute. You wait. chlorine. This is chlorine. Oxygen, 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 oxygen. 1, 2, 3, 4. Chlorine, oxygen, oxygen, oxygen. Okay, this is the structure of Cl2O7. Okay, dichlorine heptoxide. Okay, and oxygen 1, 2, 3, 4. Iodine, iodine. Oxygen, oxygen, oxygen. Sorry, iodine, iodine. Okay, oxygen, oxygen. This is I2O5. Okay, this is the compounds of halogen with oxygen and their oxidation states. Okay, as given, you can all these halogen oxide behaves as a strong oxidizing agents and get dissociated with explosion upon heating. Chlorine and chlorine dioxide and chlorine monoxide are used as bleaching agents in paper and textile industry. Paper and textile industry. Paper and textile industry. Okay, paper and textile industries, as well as purification of water. As well as purification of water. Okay, ClO2 and Cl2O are used as bleaching agent in paper and textile industries. Textile industries, as well as purification of water, purification of water. That means क्लोरीन डाइऑक्साइड एंड क्लोरीन मोनोऑक्साइड का प्रयोग कपड़े की कंपनी में और टेक्सटाइल इंडस्ट्री, कपड़े की कंपनी में और पेपर की कंपनी में उसको और जल को शुद्ध करने के लिए प्रयोग किया जाता है। किसका? क्लोरीन डाइऑक्साइड का और क्लोरीन मोनोऑक्साइड का। ओके, नेक्स्ट हेडिंग ऑक्सी एसिड्स। ऑक्सी एसिड्स except fluorine, except fluorine, all the halogens form oxy acids. All the halogen forms oxy acids. All the halogen forms oxy acids of the type HOX, HXO2, HXO3 and HXO4. Although many of these acids are known only in solution as salts, fluorine form only one oxy acid, which is a hyperfluorous acid HOF. The different oxy acids you can show. Okay, halogens HOX plus 1, HXO2 plus 2 plus third, and HXO3 plus 5 and HXO4 plus 7. Okay, fluorine, HOF, hypofluorous. This is hypofluorous, hypofluorous. Okay, this is hypofluorous. And chlorine, this is HOCl, hypochlorous, HCl, ClO3, chlorous, HClO3, chloric, this is 2, chlorous, hypochlorous, HOCl, HClO2, chlorous, and HClO3, chloric, and HClO4, perchloric, okay. Bromine, HOBr, hypobromous, HBrO2, bromous, HBrO3, bromic, and HBrO4, perbromic, iodine, HOI, hypoiodous, HiO2, iodous, HiO3, iodic, and HiO4, periodic acid, okay. Next, hypohalous acid. Okay. 1 minute. Hypohalous acid, okay. Next, hypohalous acid. 1 minute. First, hypohalous acid, okay. Hypohalous acid, okay. When halogen is passed into water, hypohalous acid along with HX is formed due to disproportionation of halogen, okay. X2 plus H2O. When halogen is passed into water, hypohalous acid along with HX is formed due to disproportion of halogen, okay. HOX plus HX, where X equal to chlorine, bromine, iodine, okay. HOX is also prepared by shaking halogen water with mercuric oxide, okay. With mercuric oxide, 2HgO plus 2H2 plus H2O, that makes HgO into HgX2 plus 2HOX, okay. Hypohalox HOX is also prepared by shaking. Prepared by shaking halogen water with mercuric oxide. Okay. Hypohalox. 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 That means HOCl, HOBr, and HOI are weak acid. Weak acid, unstable and exist in solution only, and exist in solution only, exist in solution only, okay, only exist in solution only. Salt of these acid are stable and are called hypohalites. Okay, salts of these acids, salts of these acids are stable and called hypohalites. Hypohalites are used as oxidizing agent and using oxidizing halogenating and bleaching agents okay. As example, CH3 CH2OH, okay, and oxygen and NaOCl, that makes CH3 CHO, okay, and CH3 CHO, that is chlorinating agent, chlorinating agent NaOCl, that is Cl3CCHO, okay. Among hypochlorite, sodium hypochlorite and bleaching powder CaOCl have much more commercial importance. Hyalic acid. Second, hyalic acid. Hyalic acid. Second, hyalic acid. Okay. Hyalic acid. Second, hyalic acid. Okay. Hyalic acid. Chloric acid HXO3. Hyalic acid means HXO3. Chloric acid is prepared in solution by decomposing barium chlorate with dilute H2SO4. Okay? Dilute H2SO4. BaClO3 whole twice. Okay? Plus H2SO4, that makes BaF4 barium sulfate plus 2HClO3 hyalic acid. Okay, this is hyalic acid. Okay, when barium bromate is decomposed by dilute sulfuric acid, bromic acid is formed. BaBrO3 whole twice. This is barium bromate. This is barium bromate. And plus H2SO4 decomposed dilute H2SO4 dilute H2SO4, that make barium sulfate plus 2HBrO3. This is bromic acid. This is bromic acid. This is bromic acid. Okay. And iodic acid is prepared by boiling iodine with 10 times its weight of concentrated nitric acid. 3I2 plus 10 times nitric acid, that makes 6HiO3 plus 10NO plus 2H2O. 2H2O. This is iodic acid. Iodic acid. Okay. It is also prepared by passing chlorine gas. It is also prepared by passing chlorine gas through a suspension of iodine in water that make chloric acid. Iodic acid. I2 plus 5Cl2 plus 6H2O, that make 2HiO3 plus 10HCl. Okay. Iodic acid, bromic acid, iodic acid, bromic acid are known in form of solution where is iodic chloric acid, HClO3 and HBrO3. Chloric acid and bromic acid are known in the form of solution where is HiO3 is present in the form of white solid, melting point 110 degrees Celsius. The stability of this acid increases with increase in atomic number. Atomic number increases. If atomic number increases, then stability increases. Okay. And moving down the halogen group, moving down the halogen group, and moving down the halogen group. Okay. These acids act as a powerful oxidizing agent and bleaching agent. The salts of halic acid are called halates. Sodium chlorate, NaClO3 and potassium chlorate, these are used in match industries and in explosive. Okay. For halic acid, for halic acid, HXO4, when potassium perchlorate is heated with concentrated sulfuric acid, perchloric acid is formed. Okay. 2KClO4 plus 2H2SO4, that makes 2KSO4 plus 2HClO4. Okay. When potassium perchlorate, this is potassium perchlorate, potassium perchlorate is heated with a concentrated H2SO4 perchloric acid formed. Okay. Paraperiodic acid is prepared by action of chlorine and suspension of silver mesoperiodate. Okay. Then 4Ag Ag3IO5 plus 6Cl2 chlorine gas plus 10H2 water that makes 4H5IO6. This is paraperiodic acid. Paraperiodic acid plus 12 AgCl silver chloride plus 3O2 oxygen, okay, and 2H5IO6, that means paraperiodic acid. Paraperiodic acids heated at 80 degrees Celsius temperature that make H4I2O9 dimesoperiodic acid. Dimesoperiodic acid. Dimesoperiodic acid plus 3H2O, and heating dimesoperiodic acid heating at 100 degrees Celsius temperature that make 2HIO4 plus H2O, metaperiodic acid. Metaperiodic acid, okay. The salts of perhylic acids are called perhylates. Perhylates are strong oxidizing agent. Salt of perhylic acid, salt of perhylic acid, salt of perhylic acid are called perhylates. Perhylates are strong oxidizing agent. Strong oxidizing agents. Okay, strong oxidizing agents. BrO4 negative is a strong oxidant in comparison to Cl2O4. BrO4 negative is a strong oxidant in comparison to Cl4 negative and iO4 negative. Okay, hence it is thermodynamically less stable and very unstable. Structure of oxy acids. Structures of oxy acids. Structures of oxy acids. Okay. Structures of oxy acids. Okay. Structures of oxy acid. Halogens form HOX, HXO2, HXO3, HXO4, 4 types of oxy acid. These structures of the ions are formed as you can show. Halogen, oxygen, lone pair, OX negative, okay. Halogens, oxygen, that is XO2 negative, okay. Halogen, oxygen, Okay, that is XO3. XO3. Okay, halogens, oxygens, 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 oxygens. Okay, XO4 negative. Okay, XO4 negative. Okay, XO4 negative. All the structures of oxyanions are based on tetrahedral shape. In these anions, there is sp3 hybridization. Hence, oxyanions and oxyacids show tetrahedral structures. The sp3 hybrids orbitals form only weak sigma bonds because the s and p levels differ appreciably in energy. The oxyanions are established by strong p pi d pi bonding between full 2p orbitals of oxygen and empty d orbit of halogens. Chlorine has no d orbitals, hence it cannot form p pi d pi bond. Only one acid HF of fluorine is made under special conditions, which is very unstable. All types of oxy acids have tetrahedral structures, but the shape of ClO negative is linear. ClO double negative is angular, and ClO3 negative is pyramidal, and ClO4 negative is tetrahedral. Okay. Comparative study of oxy acids. Comparative study of oxy acids. Okay. Comparative study of oxy acids. Comparative study of oxy acids. Comparative study of oxy acids. Okay. First point, thermal stability. Thermal stability. The stability of oxy acids of chlorine increases in following order. HClO is greater than HClO2 is greater than HClO3 is greater than HClO4. The stability of HXO acid increases in the following order. HClO is greater than HBRO is greater than HIO. Stability decreases and moving down the group. Stability decreases and moving down the group. Moving down the group. Okay. Second point, acidic property. Acidic property. Okay. First point, HOCl is less than HClO2 is less than HClO3 is less than HClO4. Okay. As oxidation state of chlorine increases, chlorine oxygen bond strength increases, and oxygen hydrogen bond strength decreases, and dissociation XO2XO negative plus H negative increases, and acidic strength increases. Okay. Acidic strength increases. Okay. Next point. Second point. HOBr is greater than HBrO2 is less than HBrO3. Okay. Third point. HOI is less than HiO2 is less than HiO3 is less than HiO4. Okay. And B point. First point, HOCl is greater than HOBr is greater than HOI. As the radius of X increases, halogen oxygen bond strength decreases. As the radius of X increases, X halogen oxygen bond strength decreases. Bond strength decreases, and oxygen hydrogen bond strength increases. Oxygen hydrogen bond strength increases. Show dissociation to XO negative and H negative decreases. Okay, similarly, okay, the strengths can prepare the XMOHN in M equal to 0, 1, 2, 3. The acidic is very weak. Okay, 1 minute. Oxidizing power, 1 minute. Okay, acid strength, acid strength. Okay, HOCl, this is XOMOHM. Okay, where if M equal to 0, 1, 2, 3, the acid is very weak. Okay, the value of M. Okay, and this is M. Okay, this is M, and this is the strength. Okay, HOCl, that is ClO0OH. ClO0OH. M is 0, very weak. Okay, HOBr, then BrO0OH. Okay, HOBr, okay, OH, that is 0, very weak, and HOI, that is IO0OH, that is 0, very weak, and HClO2, that is ClO1OH, that is weak, value 1, weak, and HBrO2, that is BrO1OH, that is 1, and this compound is weak, and HiO2, that is IO1OH, that is 1, and this compound is weak, and HClO3, that is ClO2OH, the value of M is 2. This is strong, okay, and HBrO3, that is BrO2OH, that is, and the value of M is 2, and this is strong, and HiO3, that is IO2OH, the value of M is 2, that is strong. Okay, next HClO4, that is ClO3 OH. The value of MH3, that is very strong, very strong. And HiO4, that is IO3OH. The value of MH3, this is very strong. And H5IO6, that is IO1OH5, the value of M is 1. This is weak compound. Okay? Oxidizing power. The oxidizing power of these acids decreases with increase in covalent property. Oxy acids of fluorine are oxidizing agents, both in acidic and basic mediums. All are strong oxidizing agents. The oxidizing power of oxy acids of fluorine is in the following order: HClO is greater than HClO2 is greater than HClO3 is greater than HClO4. This is hypochlorous. This is chlorous. This is chloric. This is perchloric acid. Perchloric acid. Okay. Perchloric acid. Okay. Acidic medium. Okay. Acidic medium. Okay. 2HClO plus 2H positive plus 2E, that is Cl2 plus 2H2O. Okay. And is plus 1.63. And 2ClO2, HClO2 plus 2H positive plus 2E. That makes HClO plus H2O, that is plus 1.65, and ClO3 negative plus 3H negative plus 2E. That makes HClO2 plus H2O, that is 1 plus 1.21, and ClO4 negative plus 2H negative plus 2E, that is ClO3 negative plus H2O, that is plus 1.19. Okay. Basic medium. Okay. Basic medium. 2ClO negative plus 2H2O plus 2E, that makes Cl2 plus 4OH negative 0.40, okay, E0, and ClO2 negative plus 2E plus H2O, that is ClO negative plus 2OH negative, that is 0.65, and ClO4 negative plus 2E plus H2O, that makes ClO3 negative plus 2OH negative, and 0.36. In basic medium, acids are as ClO negative, ClO2 negative, ClO3 negative, and ClO4 negative, but in acidic medium, HClO3 and HClO4 are ClO3 and ClO4, okay? The halic acids are strong oxidizing agents which can be arranged in the order of their oxidizing capacity. HClO3 is greater than HbRO3 is greater than HiO3. For halic acids and for halates are formed by chlorine and iodine only. Perhalic acids are more powerful oxidizing agent than the halic acids. Okay, HClO3 and HiO3. Oxidizing capacity of halogens. Next heading: oxidizing capacity of halogen. Next point, it is very important point. 4 is oxidizing capacity. Oxidizing capacity. That means power. Power of halogens. Okay, halogens. Okay, oxidizing capacity. That means power of halogens. Okay, as halogens possesses high electron affinities. Have a tendency to remove electrons. Halogens act as strong oxidizing agents. Oxidation is a process of removal of electron from an atom. The oxidizing character decreases on moving down the group. Fluorine is the strongest oxidizing agent among halogens due to its small size and high electronegativity. Oxidizing capacity decreases from fluorine to iodine. Oxidizing capacity. Oxidizing capacity decreases. Oxidizing capacity decreases from fluorine to iodine. F2 is greater than chlorine, is greater than bromine, is greater than iodine. The strength of oxidizing agent depends upon several energy terms and is represented by Born-Haber type of energy cycle. The oxidation potential E0 is the energy change between the elements in its standard state and its hydrated ions. Hence, the energy released in conversion of halogen into hydrated ions X negative equivalent is the measure of its oxidizing capacity. Okay, half halogen plus electron oxidizing potential. Oxidizing potential, that is X equivalent. Okay, the above process involves many energy steps which you can show that that is fluorine, chlorine, bromine and iodine. Okay, that is reaction half X2 and solid, that make half X2 liquid. Fluorine X and half delta HF. Okay, that is 0, 0, 0 and 1.8. Okay, and half X2 liquid, plus that makes half X2 converted in gas, that is X and half delta HV and half delta HV, that is 0, 0, 3.7 and 5.2, and half halogen gas is converted is also X halogen gas, that is half delta HD, half delta HD and half delta HD and half delta HD. Okay, that is 18.75, 28.55, 23.3 and 17.85. Okay, and halogen is gaseous state is converted in a halogen gaseous state negative ion plus electron release, that X negative and gas, and this is electron affinity EA, electron affinity EA, electron affinity EA and electron affinity EA. The value of electron affinity is minus 83.6, minus 89.6 and minus 82.2 and minus 75.6. And gaseous halogens of gaseous state negative ion. Halogens of gaseous state negative ion is aqueous. Converted is halogens of negative aqueous equals is delta H Hy delta Hy delta Hy and delta Hy is minus 122 minus 89 and minus 81 and minus 72. Okay, and after this final is half x2 plus e to x negative equals delta h e naught in bold that is delta h delta h delta h delta h delta h and delta h and delta h that is minus 186.5 and minus 147.4 and minus 136.4 minus 122.8 electron volt, 2.87 electron volt, 1.30 electron volt, 1.07 electron volt and 0.54 electron volt. The highest E naught of fluorine is due to high delta Hy of fluorine. The lowest value of E naught for I2 is due to delta HF, delta Hi and low delta Hy. Thus oxidation potential. E naught. 1 minute. Oxidation potential E naught equal to delta HF plus delta HV plus delta HD minus electron affinity minus delta Hy. Okay, where E naught is oxidation potential, net energy. Oxidation potential, net energy, oxidation potential, net energy, delta HF, heat of fusion, and delta HV, heat of evaporation, heat of evaporation, and delta HB is a heat of dissociation, heat of dissociation, heat of dissociation, and EA is electron affinity, and delta HY is a heat of hydration, heat of hydration, and unit of delta H is kilocalorie per mole inverse. Okay, from the expression of oxidation potential E naught, it is clear that in first 3 steps energy is absorbed while energy is released in last 2 steps. The lower will be the value of E naught, the higher will be its oxidizing capacity. If E naught is lower, if E naught is lower, then oxidizing capacity is higher. Oxidizing capacity is higher. Okay. For fluorine, chlorine, the value of delta HF, delta HY, delta HB are 0. For fluorine and chlorine, the value of delta HF and delta HB is 0. Okay, as the value of E naught is less, but it becomes more due to their electronegativity and high hydration energy of their ions. In case of bromine, which is liquid at room temperature, the delta HF has been omitted. Okay, the value of E naught is maximum in case of fluorine and gradually decreases down the group. That is why fluorine is strongest while iodine is weakest oxidizing capacity agent. Hence, it is the oxidation potential and not the electron affinity alone controls the strength of oxidizing agent. This is the reason that chlorine, which has the maximum electron affinity value, is not the strongest oxidizing agent. Some important reaction of halogens you can list that. Okay, okay. 1 minute. H2 plus X2 2HX with all halogens. Okay, and H2O plus X2, that is 2HX plus half O2 with only with fluorine F2 and H2O plus X2, that makes HX plus HOX, that is with only with chlorine and bromine, chlorine and bromine, and 2 mg plus X2, that is 2 mgx with all halogens, and 2 iron ferrous plus 3 X2 and 2 FeX3, that is with all halogens, with all halogens, okay, all halogens, okay. X2 plus CO, that make COX2 with only with chlorine and bromine, and 3X2 plus 2 phosphorus, that make 2PX3 only with all halogens, and 5X2 plus 2P, that make 2PX5, that is only with chlorine and bromine, and X2 plus 2S, that make H2X2 and with chlorine and bromine, Next is Cl2 plus S, Cl2 plus S, S, that make SCl4, only chlorine, okay, and 3F2 plus sulfur, that is sulfur hexafluoride gas, SF6, that is fluorine only, and H2 plus H2S, that make 2HX plus S with this is reacted with all halogens, and H2 plus SO2, that make SO2 X2 reaction with only fluorine and chlorine. 3H2 plus nitric acid of 8 molecules, NH3 ammonia, NH3, okay, NH3, 8 ammonia, that react, and nitrogen gas plus 6NH4X reacted with only fluorine and bromine, and X2 plus X2 dash, that is 2XX dash, that is interhalogen compounds, interhalogen compounds, and X2 plus X dash X, that is X dash X3, higher interhalogen compounds, higher interhalogen halogen compounds, higher interhalogen compounds, 2OH plus H2, X negative plus XO negative plus H2O. That is with chlorine, bromine and iodine. Chlorine, bromine and iodine. This is chemical properties of the halogen groups is ended, and next heading is gradation in properties. Gradation in properties. Okay.